Welcome to Tiny Teeth Talks. Today we are not doing Savaal Saturday, but we are doing solutions which include MCQs on digital radiography in pediatric dentistry. Today we are going to discuss that MCQs with the correct answers and explanation. So let's start with the first MCQ. The first digital imaging system RVG was introduced by, here you can see this, AIMS 2012 and PGI 2015. So, if any question asked previously in any competitive exam, I already mentioned after that individual question. So, you can easily get an idea of what type of question can be asked. So, the answer is B. Dr. Franz Moen, who invented RVG in 1987, the first digital dental X-ray. Let's do this like a MCQ paper. Okay, so what we do in the exam, that we eliminate the answers first. Okay, so let's see why not others. So starting with the A. William Rontgen. William Rontgen discovered X-rays in 1895. Then C. F.W. McCormack. So Franklin Wentworth McCormack, he applied the geometric principle of parallelism to dental imaging in 1920, established a paralleling technique as a practical method for reducing dimensional distortion. And D. C.Z. Fitzgerald. Gordon Merritt Fitzgerald, known as the father of modern dental radiography, he redefined the paralleling technique in 1947 by introducing long cone open-ended position indicating device to produce more accurate parallel X-ray beams. So that's why the correct answer is B. Next question. Which digital sensor technology utilize a latent image that must be scanned by a laser? So if we see this question, then first its click answer is C. Photostimulable phosphor plate, because it requires scanning by the laser to generate the X-ray. So why not others? Because in case of CCD and CMOS, they are the direct digital sensors. They don't need any latent image. They do instant data transfer and create the image, while phosphor plates required scanning and form the latent image by storing the X-rays, and then it scanned by the laser which generate the image. If you talk about option D, flat panel detector, so in CCD CMOS, sensors are primarily used for intraoral inside the mouth imaging. Flat panel detectors are the standard for extraoral imaging such as a cephalometry, panoramic and CBCT scan. So the answer is C, photostimulable phosphor plate. Then the next, in digital radiography, the term pixel is an abbreviation for, so here abbreviation means short form or a phrase of that word. So the answer is picture element. Now see why. So pix is the shorthand of pictures and L is a shorthand of element. So picture element. For your kind information, pixel is the smallest unit of digital image. So why not other? So let's say other option. So B is picture matrix. So a matrix is the entire grid which has a rows and columns of pixels, not a single element. If a pixel is an individual brick, then the matrix is the whole wall. So no matrix. So cancel picture matrix. Then see digital point. So this is the descriptive term but not the formal abbreviation. And binary unit, the unit that computer use. So the option A is the correct answer. Then the next, which of the following is an advantage of PSP plates over CCD and CMOS sensors in pediatric dentistry? So the correct answer is greater flexibility and similarity to conventional film. In pediatric dentistry, the small size of the oral cavity and the presence of a gag reflex makes sensor placement difficult. PSP gives comfort because they are thin and flexible, and unlike rigid CMOS sensor, PSP plate can be slightly curved to fit the narrow pediatric arch or to avoid hitting the floor of the mouth, which reduce the discomfort for the child. Plus, because the lack of a bulky cable and have a physical profile almost identical to traditional X-ray film, they are much easier for a child to tolerate. And PSP plates come in a wide range of size, including 0 for very young children that are much thinner than the digital counterparts. So that's why it creates greater flexibility and similarity to conventional film. Let's see other options. So A, real-time image display display. So this is actually a disadvantage because we know that PSP requires scanning. Then wireless connectivity is always inherent. This is technically incorrect. While PSP plates does not have wires during exposure because they aren't connected to the computer, they physically placed in a scanner. D is high spatial resolution. So this is the disadvantage of PSP. PSP lose some detail because the light spreads slightly during the laser scanning process, leading to a slightly blurrier image compared to high and direct sensor. Next, the dynamic range of a digital sensor refers to what? This is basically a definition that dynamic range is the range of exposure that produce a useful image. Let's see other option. So speed at which the image is processed. No, this referred to the readout time or latency. So cancel. The range of exposure that produce a useful image, which is the correct answer. The physical size of sensor. So this is simply the dimensions or active area of the sensor. Then the number of the shades of the gray. So this is very common distractor. So you might distract here. That might be the number of shades of gray. But no, while bit depth, which is known as a contrast resolution, determines how many shades of gray the computer can display, while the dynamic range determines how much radiation the sensor can capture before it fails to show details. Option B is the correct answer. Let's see the next. Which imaging modality is most suitable for evaluating 3D position of an impacted supernumerary tooth in child? So here you generally encounter that CBCT is the 3D imaging. So the answer C, CBCT. It provides cross-sectional slices and these allow the surgeon to see if the tooth is positioned labially or palatally. Why not others? So OPG is a 2D scan. So while it can tell you the supernumerary tooth is present, it cannot reliably tell if the tooth is in front or behind the other teeth. It also suffers from magnification and distortion. When we talk about lateral cephalogram, it's also side view of 2D X-ray. It's useful for the orthodontic growth analysis, but the teeth on the left and right side overlaps, making it useless for pinpointing a specific impacted tooth position. Then digital bitewing. These are designed to detect the interproximal caries and bone levels. The film is not placed high enough in the vestibule to capture the crown or root of an impacted supernumerary tooth. So option C is the correct one. Next, the blooming effect is a phenomenon specially associated with which type of digital sensor? Here the answer is CCD. Let's see how. So blooming is specific artifact seen in charge couple device sensor and the excess electron spills over the neighboring pixels creating a smear, or you can see the bloom of the white light. You can see the bloom of the white or bright light on the image. So in dental radiograph, the blooming effect is most obvious around the objects that are extremely radio opaque. So how to identify this in a dental x-ray? So look at the edges of metal crown, amalgam filling or implant. Instead of sharp crisp lines separating the metal from the tooth or bone, you will see a bright white glow or a cloud bleeding into the adjacent structures. In some CCD sensors, this appears as a vertical white streaks like a light beam coming off the metal objects. So the bloomed white area covers up important details. For example, if you are looking for a recurrent caries under the margin of the crown, the blooming halo will hide the dark spot of the cavity, making the tooth look healthy when it isn't. So that's why it's the artifact of the charge couple device. So option B is the correct one. Next, the step wedge used in a digital radiography is primarily intended to calibrate what? So the answer is contrast and grayscale level. So let's see what is step wedge here. It is a small block of aluminum shaped like a staircase steps. Usually it has about 8 to 12 steps where the first step is very thin and the last step is very thick. How does it work? So when you take an x-ray of this metal staircase, the x-ray pass through it differently. In thin steps, most x-ray pass through, so this makes the image look dark or black, and in thick steps, most x-rays are blocked by the thick metal, so this makes image look light or white in that area. And middle steps, you get various shades of gray. Why do we use it? So we use it for the quality control to ensure the image density and contrast contrast are correct. So the primary job of step wedge is create a predictable staircase of gray levels. Since each step has a known thickness which is 1 mm increments, it should absorb a specific amount of radiation. So to check the calibration of contrast, if your sensor or monitor is working correctly, you should be able to clearly distinguish between each step. For calibration of density, it checks if the darkness of the image is consistent. For example, if you take the same X-ray today and in a month, the middle step should be exact same shade of gray. If it isn't, your X-ray machine or sensor is losing sensitivity. So it is used to check the contrast and gray levels, which is density. So option C is the correct. Let's see why not others. Option A, vertical angulation. So vertical angulation is a geometric factor, and to calibrate these you use the position devices or the rule of the isometry. So cancel. Spatial resolution. Spatial resolution is about how sharp an image is, and exposure time is the setting on the X-ray control panel. That's why option C is correct. Next, in digital subtraction radiography, what is the primary clinical use in pediatric periodontics? When we see this periodontics word, we generally select the B, monitoring minor alveolar bone changes over time, and this is the correct answer. Let's see what is digital subtraction radiography. So it is a high-tech process where computer subtracts one image from another to show only the differences. So you take a baseline X-ray of a patient, months later you take second follow-up X-ray in the exact same position, and the computer removes or subtracts everything that stayed the same. So the result is only the areas that change, like bone loss or bone gain, show up the bright or dark spots. In periodontics, it is the most sensitive way to detect the bone loss. That's why answer B, monitoring minor alveolar bone changes over time, is the correct one. But let's see like a exam question and eliminating the other one. So let's see why not others. So detecting caries. While DSR can track caries progression, but its primary fame and main clinical use in specialty exams is for bone density changes. See, in dipple position and root canal, so these are the static measurement. You don't need subtract two images to see where a pulp is or how long a root is. Single high quality digital X-ray is sufficient. Next, which of the following is a dead pixel in a digital sensor? Option B is the correct one. Let's see how. So dead pixel is a manufacturing defect or a result of wear and tear on a digital sensor like CCD and CMOS. So let's see the mechanism. Each pixel is like a tiny light or X-ray sensor. If the tiny transistor for that specific pixel breaks, it stops working, it becomes stuck, and there is a black and white dot. Black dot in which condition? So when pixel is off and provides no data, and white dot because the pixel is short circuited to on position and showing maximum brightness regardless of X-ray dose. Let's see why not others. So overly sensitive. So overly sensitive is called the hot pixel. It's not dead, it's just loud and create noise, especially when the sensor gets warm. Wireless transmission pixel captures light and X-ray. They are not used for transmitting data. Wires and Wi-Fi chips handle the transmission, only detect X-ray but not light. So this describes the nature of different sensor type, direct or indirect, but isn't a definition of a broken pixel. So the correct answer is B, the pixel that does not respond to radiation, appearing as a consistent white or black dot. Next, the ghost image in a digital panoramic radiograph is characterized by option B, being higher than the real object and on the opposite side, is the correct answer. Let's see how. So ghost image is a unique artifact in the panoramic image caused by the path of rotating X-ray beam. It occurs when a very dense object like a earring, lead apron or spinal column is located between the X-ray source and the center of the rotation. Now the X-ray beam in the panoramic machine has a negative vertical angulation. Because of this geometry, an object on the back side of the patient is projected higher onto the sensor or a film on the opposite side. So opposite side, if a patient wears an earring on the right ear, the ghost of that earring appears on the left side of the OPG. Higher, it appears higher than the original real image. Blurred or magnified, it appears significantly larger and much blurrier than the real objects. Let's see why not others. Option A, same side. So real images are on the same side. The ghost images are always contralateral. We already discussed this. Sharper, ghost images are blurred, not sharper. So eliminated these. And also D, lower, because of the upward downward tilt of the beam, the ghost is always projected higher. Let's see next. Which digital radiographic feature allows the clinician to change the darkness or lightness of the displayed image without re-exposing the patient? So option B, histogram equalization, is the correct answer. Let's see how. So one of the greatest benefit of digital radiography is post processing, which lets you fix a bad image without exposing the patient to more radiation. So histogram equalization, which is also known as a windowing or leveling, allows the computer to redistribute the pixel values. So leveling is used for the brightness and windowing is used for the contrast. So that's why histogram and equalization. Let's see why not others. So first, digital subtraction. Digital subtraction we already discussed that it used to find the changes over time, not just to brighten an image. Then option C, edge enhancement. This is a sharpening filter. It makes the border of the structures look more distinct but not primarily adjust overall brightness. And the D inversion, this flips the image polarity. What was white becomes black and what was black becomes white. It is useful for finding fine files in a root canal but isn't for the standard brightness adjustment. That's why option B is the correct answer. Next, the active area of digital sensor is usually option C, smaller than the outer dimension, is the correct answer. Let's see how. Every digital sensor has a plastic or metal housing that protects the internal electronics and sensitive silicon chip. This casing plus the internal wiring takes up the space. Therefore, the actual area that captures the X-ray is always smaller than the physical outer dimension of the sensor. That's why the active area of digital sensor is usually smaller than the outer dimension. Let's see why not others. So option A is larger than the outer dimension and option B is equal to the outer dimension. It is physically impossible for the capturing surface to be larger than or perfectly equal to the outer shell, as the shell has a specific thickness for protection and rounded corners for patient comfort. And option D is unrelated to clinical use. So it is highly related to clinical use. A sensor with a small active area relative to its size forces the dentist to take more images to cover the same anatomy. Next, which of the following digital system requires a processing step in a laser reader? We all know that PSP plates. So as we discussed earlier, plates store energy in the crystals. To see the image, the plate must be placed in the scanner where the laser stimulate the plate to release the light, and this is why the PSP is called indirect digital imaging. That's why the answer is next. In digital imaging, spatial resolution is primarily determined by, correct answer is B, pixel size. So spatial resolution is the ability of the system to distinguish between two objects that are very close together. In digital imaging, this is limited by the size of pixel. So if there is a smaller pixel, then high resolution, more detail, and larger pixel, lower resolution and grainier or the blackier image. So it's related to the pixel size. So answer B, pixel size, is the correct answer. Let's see why not others. So option A is bit depth. So bit depth determines the contrast resolution. So how many shades of gray? So eliminated. Then option C and D, exposure and KVP. So these affect the quality and noise of the image. So answer B is the correct one. Let's see next. So the process of converting analog signal to digital signal is known as option B, sampling and quantization, is the correct answer. So let's see how. So an X-ray starts as an analog signal. To make it digital, the computer must do two things. First, sampling. The computer looks at the image at a specific intervals, which creating the pixel grid. And then quantization. The computer assign a specific numerical value to the brightness of each sample. A, modulation. So modulation is referring to the changing a signal to carry information. Then option C, filtration. This is the process of removing low energy X-rays from the beam using aluminum disc to protect the patient. So eliminated. And enhancement, this happens after the image is already digital. So D is eliminated first. Then filtration is also eliminated because it is used for removing low energy X-rays. And you can be confused between A and B, but A modulation is referred to changing a signal to carry information. So for complete analog to digital, computer need to do sampling and quantization. So option B is the correct one. Then next, which sensor type is most likely to suffer from bulky dimension and rigid cable? If CCD was the option here instead of CMOS, it is also correct. Let's see how. So CMOS or CCD are direct digital sensors, and because they contain silicon chip, a circuit board and protective housing, they are significantly thicker than the film, and furthermore they require a rigid cable to transmit data instantly to the computer. Okay, so the CCD or CMOS are the correct answers. So answer B is the correct. Let's see why not others. So PSP, these plates are thin, flexible and have no cable, so cancel. They are designed to feel like a traditional film. Then traditional film is the thinnest film we know, and they have no digital cable, so eliminated. And between tabs, they are just a paper or plastic stickers holders used to position the sensor. They are not sensor themselves, so eliminated. So easy answer. Next, what is the standard bit depth for a system displaying 256 shades of gray? So the answer is B, 8-bit. Let's see how. Okay, so in digital system, data is stored in binary. The number of available shades of gray is calculated as 2n, where n is the number of bits, so it's like 2 raised to n. So if there is a 4 bit, so 2 raised to 4 is equal to 16 shades, and 12 bits, so 2 raised to 12 is to 4096 shades, which is common in high-end CBCT and direct sensors. And if there is a 16, so 2 raised to 16, which is 65536 shades, and our answer is 2 raised to 8, so 256 grades. Next, dithering in digital imaging refers to option B, a method to simulate more colors grays than the system can actually display. Let's see how. So sometimes a computer monitor or a printer cannot show all 256 shades of gray at once. So if the system can only show pure black and pure white, an X-ray would look terrible and lose all the details. By using dithering, the software creates stippled or speckled pattern of black and white pixels. These make the image look like it has a smooth gray transition, allowing the dentist to see the subtle borders of cavity or a root canal even on a low quality screens. Answer B is the correct. Let's see why not others. So option A is type of noise. So noise is random and make the image look grainy and bad because there weren't enough X-rays. Dithering is a calculated pattern used to make the image look better. Then option C, vibration of the tube. So these cause the penumbra, blurring of the edges, make the image look fuzzy. It has nothing to do with the creating gray levels. And option D, a sensor defect. A defect is an error in the hardware. Dithering is a software feature designed to help display the image. So that's why answer B is the correct one. Next, the theoretical resolution of digital sensor is measured in option B, line pairs per millimeter is the correct answer. Let's see how. So what is line pair? So to test how sharp a sensor is, we use a tool called line pair phantom. It is a piece of lead with tiny slits cut into it. So one line pair is equal to one black line and one white spaces. To the computer, it's just detail. Then what does per millimeter mean? So imagine you have a tiny space only 1 millimeter wide. So if a sensor can only fit 5 line pairs in the 1 millimeter before they all blur together into one gray blob, it has a low resolution. And if sensor can fit 20 lines pairs in the same 1 mm and you can still see each individual line clearly, it has a high resolution. So we use line pair per millimeter to measure the theoretical resolution of digital sensor. So option B is the correct one. Let's see why not other. So A and C, pixel per inch and dots per inch. So these terms are used for printers and computer monitors, not the raw capturing capability of a medical X-ray sensor. And option D, megabits. This is the unit of data transfer speed or the file size, not the image sharp. Next, which of the following is not a component of CMOS sensor? So option C is a developer solution. You can easily crack these. That developer solution is a chemical used in a dark room to process the traditional X-ray film. That's why option C is the correct one. Next, a major advantage of a digital sensor in pediatric trauma cases is option B, near instantaneous image display. So let's see how. So in trauma case, if a child has fallen and broken a front tooth, the patient is usually in pain, crying and uncooperative. The ability to see the image on the screen immediately allows the dentist to diagnose the fracture or a luxation quickly and begin the treatment without waiting for the film to develop. That's why answer B is the correct one. Why not others? They are unbreakable. Digital sensors are actually very fragile and expensive, and if a child bites down hard on CMOS sensor, it can break the internal silicon too. So eliminated first. Then they require no radiation. Digital sensor reduce the radiation by 50 to 90%, but they still require X-rays to work. So eliminated. They are much cheaper than film. No, they cost more than traditional film and high cost itself. So answer B is the correct one. Next, in pediatric endodontics, digital radiography is superior for what? So option A, measuring working length via measurement tools is the correct one. Let's see how. So digital software include a ruler tool. During a root canal, the dentist can click on the incisal edge and drag to the apex of the tooth. The computer calculates the exact length in the millimeters. So in traditional film, the dentist had to use a physical ruler against a tiny piece of plastic, which is much less accurate. That's why measuring working length. Let's see why not others. So option B, identifying accessory canals. So while digital is clear, accessory canals are often so tiny they are missed by both the film and two digital sensors. We need CBCT for this. So option B is cancelled. Option C, reducing movement. The sensor doesn't stop the child from moving. In fact, the bulky cable might make them move more than thin film would. So eliminated. Then D, eliminating rubber dam. So rubber dam is mandatory for safety in endodontics to prevent the child from swallowing small files. Digital X-ray do not change this safety rule. Next, which digital modality is best for diagnosing a mesodense? Option C is CBCT. Let's see why. Mesodense is a supernumerary tooth located in the midline of the maxilla between the central incisor, and it is often impacted and can be inverted or positioned palatally. So CBCT provide 3D views which are essential for surgical planning to avoid damaging vital structures like nasopalatine canal. Option A, panoramic. It is good for journal survey, but it suffers from superimposition in the midline, and 2D view do not give clarification. Then bite wing, designed for detecting decay between posterior teeth, and it doesn't even show up the root tips of the anterior midline clearly. Lateral ceph, again used for orthodontic measurement of the profile. It shows the tooth from the side, but it isn't useful for the exact surgical localization. Let's see next. To reduce gagging in pediatric patient while taking a digital IOPA, you should option B, start with the anterior teeth is the correct one. So let's see how. So the gag reflex is strongest in the posterior part of the mouth, which is the soft palate and the back of the tongue. So by starting with the anterior teeth, you allow the child to get used to feel of the sensor in a safe zone where they are less likely to gag. So to eliminate the least anxious element first, which leads to desensitization. So this build trust and desensitize the oral mucosa before you move to the sensor towards the more sensitive posterior regions. Let's see why not others. So start with the most posterior teeth. So this is the quickest way to trigger a gag reflex, which will make the child refuse the rest of the x-rays. Then option C, largest sensor. Largest sensors are bulkier and more likely to touch the trigger zones of the throat. So cancel. Then option D, it will hurt. This create anticipatory anxiety, which actually lowers the gag threshold. So that's why option B, start with the anterior teeth, is the correct answer. Next, digital subtraction radiography is particularly useful in pedodontics, for we know that monitoring bone gain after the regenerative procedure. Option A is the correct one. So as we learned, DSR is the gold standard for seeing changes over time in pediatric dentistry. It is used after trauma or regenerative surgery like apexification or bone grafting to see if new bone is forming. So let's see why not other. So first sign of cavity, while it can track decay, standard digital bite wing with enhancement filters are the routine choice of initial diagnosis, or not DSR to see the first sign of cavity. Then Then identifying tooth gum, you can see the tooth gum on any standard x-ray, you don't need to subtract the image to find it. Then pulp chamber size, it's a static measurement easily done with the standard digital measurement tool. That's why option A is the correct one. Next, which of the following reduce the patient dose the most in the digital system? So option B, using a rectangular collimator, is the correct one. Let's see how. So collimation is the process of restricting the size and shape of the X-ray beam. So a standard round X-ray tube cone produces a beam that is much larger than a rectangular digital sensor. So this means a lot of excess radiation hits the patient's cheek and thyroid without ever touching the sensor. So switching to the rectangular collimator matches the beam to the exact shape of the sensor, and this reduces the area of the patient's skin exposed to the radiation up to 60 to 70%. So option B, using a rectangular collimator, is the correct one. Let's see why not other. So increasing milliampere, this increases the number of X-ray photons, which also increase the patient dose. So cancel. Using the enhanced filter, filters happen after the X-ray is taken. They improve the look of the image but do nothing to change how much radiation the patient received. Then skipping anterior teeth, while fewer shots technically means less dose, so it is not a system feature for reduction. Here don't confuse with the two numbers. This is because I made a mistake in numbering in uploaded Saturday question. So today in this PDF I also gave correct number on the left side, and according to previous PDF numbers are in bracket. Okay, let's see next. The most common artifact in the pediatric digital radiography is option B, motion blur. Children are naturally visually anxious and may have a difficulty holding their breath or staying still for even 0.5 seconds required for an exposure. Even a tiny movement of the head or the sensor during the firing of the X-ray cause the image to appear fuzzy or blurred or often require a retake. That's why option B is the correct one. Let's see why not other. So ghost image. So these are common in OPG X-ray, but motion blur happen in every type of X-ray. Option C, scratched PSP plates. So this is common problem with PSPs, but it's a hardware maintenance issue, not a patient related artifact. And D, electrical noise. So this is usually result of a sensor getting too old or hot. It is far less common than a child simply moving. So option B, motion blur, is the correct answer. Next, the phosphor used in PSP plate is usually a barium fluoride with europium. Option B is the correct one. So the crystals are made up of barium fluorohalide. Europium is the activator that creates the traps or the holes that catch the X-ray energy. When the laser hits these traps later, they release the light which the computer turns into the image. Let's see why not others. So silver halide is the chemical used in traditional film, not digital plates. So cancel. Calcium tungsten, this was used in old fashioned intensifying screen for extraoral film but not used in the digital PSP. So cancel. And the rare earth elements are not related to this question. Next, which filter is used to smooth a grainy digital image? Option B, low pass filter, is the correct one. Let's see how. So in digital imaging, noise or grainness, which is known as quantum motile, is considered high frequency data. So a low pass filter allows low frequency data to pass through while blocking the or blurring the high frequency noise. Result, the image looks softer or smoother, though you might lose a little bit of sharpness in the image. So that's why low pass filter for the smooth or grainy digital image. Let's see others. So high pass filter. So high pass filter does the opposite. It removes the smooth area and keep the sharp edges. It makes an image look sharper or crispier but makes noise even worse. Then median filter. This is specifically used to remove the salt and pepper noise rather than the general graininess. And edge enhancement. So this is the high pass filter variant used to make root canals or fractures stand out. It does not smooth the image. Then next, identify the artifact in the PSP image which shows the sharp straight white line cutting across the image. So this is the scratched phosphor plate. So option C, scratch phosphor plate, is the correct one. So white line mechanism. A scratch physically removes the phosphor crystal from the plate. Since since there is no phosphor in the specific area to trap the electrons and later emit the light during scanning, the computer receives a signal of zero light for the coordinate, resulting in sharp crisp white line. Let's see why not other. So patient movement, it caused the blurring or the double outline, not the sharp straight line. Then static electricity, it's usually appear as a tree like or smudge black pattern on traditional film. In digital it's less common but looks like a random noise. Then double exposure result in the two overlapping anatomical images, making the image look cluttered and dark. Next, in CCD sensor, which layer is responsible for converting X-ray photons into visible light photons? So the answer is scintillator layer. So a CCD is designed to detect visible light. To make it work for dental radiography, a scintillator, which is usually made up of cesium iodide or gadolinium oxysulfide, is placed on top. When X-ray photon hit this layer, the material fluoresces and converting high energy X-ray into low energy visible light photons that the silicon can actually see. So let's see why not others. So a silicon wafer, this is the photodetector. It converts the visible light into the electrical charge. It cannot convert X-rays directly with the high frequency. Then option C, fiber optic plate. So these layer act as a bridge. It funnels the light from the scintillator down to the silicon wafer while shielding the silicon from direct X-ray damage. It does not convert energy, it only directs it. Then discrete capacitor. So these are tiny wells within the silicon pixels that store the electrical charge until the image is read out. That's why answer B, scintillator layer, is the correct answer. Next, which component of a CMOS sensor allow it to have a lower power consumption compared to CCD? So option B, active pixel sensor technology with individual transistor, is the correct one. The fundamental difference lies in how the electrical charge is handled. So in CCD, every pixel's charge must be physically shunted or move across the entire chip to single output corner. So these require high voltage clocks to move the charge, which consumes significant power and generate hits. In CMOS, each CMOS pixels has its own individual transistor built right into the pixel itself. So this is called active pixel sensor technology, which is seen in CMOS. So because the conversion from the charge to voltage happens locally at the pixel site, the chip does not need to move massive amounts of charge across the long distance. It can read pixels like a computer reads RAM using much lower voltage and power. So option B, active pixel sensor technology, allows CMOS to have a lower power consumption. Why not others? So larger pixel size. Okay, so while larger pixels can catch more light, they actually increases the capacitance and can sometimes require more power to clear the charge quickly. Then option C, external ADC. So having an external converter would actually increase the power consumption due to the energy needed to transmit analog signals off chip. So modern CMOS sensors are efficient specifically because they have internal or on-chip ADCs and thicker scintillator. These affect the image sensitivity and resolution but has no direct impact on the electric power consumption of the sensor circuit. Next, in photostimulable phosphor technology, the F center or the color center are located within. So option B is the correct answer. The magic of PSP plates happen in the phosphor layer. The layer consists of the barium fluorohalide crystals. So what is F center? So F center mechanism, when X-rays strike this crystal, they knock electrons loose. Some of these electrons get trapped in the halogen vacancies, and these specific sites where an electron is trapped are called the F centers. F centers are located within these europium doped barium fluorohalide crystals. Let's see why not others. Option A, aluminum backing. This is a structural or protective layer at the bottom of the plate to provide rigidity and reflect the light. It contains no crystal for electron trapping. Then polyester base. So this is the plastic substrate that supports the phosphor coating. It's chemically inert and does not have any crystal lattice capable of forming F centers. So eliminated. Protective top coat. So this is the thin clear polymer layer designed to protect the phosphor from scratches and moisture. It does not participate in the X-ray energy storage process. Next, what is the function of anti-halo layer in a digital phosphor phosphor plate. So option B, to prevent light reflection back into the phosphor layer, is the correct answer. So in PSP technology, the image is read by a scanning laser. When the laser hits the phosphor crystal, they emit blue light. However, this light can spread laterally or reflect off the back support layer of the plate. First, understand what is the halo effect. So if the emitted light reflects back into the phosphor layer, it creates the halo or a blurry glow around the actual data point, and these result in the loss of image sharpness. So for that we need the anti-halo layer. It's called the color layer. Is a light absorbing layer located between the phosphor and the support base. It absorbs the laser light and prevents it from reflecting back up, ensuring that only the light intended for the photodetector is captured, thus keeping the edges of the image crisp. Let's see why not others. So A, radiation sensitivity. This is determined by the thickness and composition of phosphor layer, not the anti-halo layer. Then saliva protection. This is the job of the barrier envelope used during the clinical procedure. So eliminated. Flexibility. The plate's flexibility comes from the polyester support base. Next, when using a handheld X-ray unit in pediatric dentistry like NOMAD, the backscatter shield must be option C, held at the outer end of the cone to create zone of occupancy. Here is the NOMAD are unique because the operator stays in the room. Protection relies on the lead impregnated acrylic backscatter shield. You can see in the second image here, external backscatter shield. So when the shield is positioned at the very end of the cone, you can see in the image, which is closest to the patient, it creates a cone shaped shadow of protection behind it. So if the operator stand directly behind the device with the shield perpendicular to the beam, they are inside this safe zone where the radiation exposure is negligible. So that's why it should be held at the outer end of the corner to create a zone of occupancy, is the correct answer. Let's see why not other. Remove for better visibility. Never. Removing the shield removes the operator's primary protection against the backscatter. So cancel. Held perpendicular to the operator. The shield should be perpendicular to the X-ray beam to block the backscatter coming from the patient's face toward the operator, not perpendicular to the operator. Option D, used only with the lead aprons. So while lead aprons are a great secondary precaution, the backscatter shield is the primary requirement for the device designed to be considered safe for handheld use. Next, identify the artifacts in the panoramic image where the palate appears as a thick radio opaque horizontal line obscuring the maxillary root. Okay, you can see the maxillary root tips are black, so this creates some space, and above that there is a white line which is the thick palate. Okay, so answer B, tongue was not pressed against the palate, which is tongue down error, is the correct answer. This is the most common positioning error in panoramic radiography. For a clear image of the maxillary teeth, patient must swallow and hold the dorsum of the tongue firmly against the hard palate throughout the exposure. So if the tongue is not touching the roof of the mouth, a pocket of air remains. This is known as a palatoglossal air space. You can see in the image the black space. Then result, air is very radiolutioned. In a panoramic sweep, this dark air space is projected directly over the apices of the maxillary teeth. And the thick line, the contrast between the very dark air space below and the dense radio opaque hard palate above makes the palate look like a sharp, thick, floating horizontal line that cuts off the view of the upper roots. And this happens when tongue was not pressed against the palate. Why not others? So option A, patient tilted their head down. So if the chin is too low, you can see this exaggerated smile in this image. It is also cause the mandibular incisor to appear blurred and the hyoid bone to superimpose over the mandible. It doesn't create a horizontal line over the upper roots. Okay, you can see the upper roots here. So patient was wearing a necklace or jewelry. So necklace or jewelry creates the ghost image because the X-ray source rotates a metal object on the patient's neck, ear or nose appears twice, and once a sharp image on the side it's on, and once as a blurred large higher position ghost on the opposite side, it typically appears at bottom of the image not across the maxillary apices. So you can see here a panoramic radiograph with a metal sphere attached in the region of the hyoid bone show two real and bilateral images and one ghost image in the center of the image receptor. Then option D, slumping of the shoulder. So these cause the cervical spine to be projected as a radio opaque vertical pillar in the center of the image. You can see here the pyramid structures. It obscures the anterior teeth but does not form a horizontal band across the entire maxillary arch. The cervical spine is slumped, appearing as a pyramid shaped opacity center at the lower half of the film. Next, the aliasing effect in the dental imaging appear as a moire patterns occurs when these lines you can see in the image are the artifact known as a moire pattern. So it is because a sampling frequency is less than twice the highest spatial frequency. Let's understand this. So this is based on the famous rule in physics and signal processing called Nyquist-Shannon sampling theorem. So the rule is to capture a digital image accurately without any fake patterns, you must sample at a rate at least twice the highest frequency of the object you are x-raying. This minimum rate is called the Nyquist frequency. So what happen in aliasing effect? So if the object has a very fine repetitive details like the lead strips in an anti-scattered grid that are smaller than 2 pixels wide, the sensor gets confused. It cannot accurately map the high frequency pattern, so it aliases means it maps that data into a much lower frequency. The result is you see the Moir patterns. These are the wavy, watery or grid like lines that don't actually exist on the patient but appear on the screen because of this mathematical mismatch. Let's see why not others. So patient moving during CBCT scan, so this causes motion blur or ghosting, but it does not create geometric wavy Moir pattern. Then option C, pixel size is too large. While larger pixels cause a lower sampling frequency, the reason the artifact appear is the violation of the Nyquist limit, not just the size itself. So you can have a larger pixel and no aliasing if the object doesn't have a fine repetitive patterns. Then option D, the KVP is too low. Low KVP affect the contrast and may increase quantum model, but it has no effect on spatial sampling frequency. Next, identify this specific digital sensor type which lacks a cable and is processed in a drum or a slot scanner. You can easily say PSP, okay, because CCD and CMOS have direct digital imaging quality, while in PSP you have to put it in a scanner and laser scan and then produce the image. And option D, fiber optic sensors is a component inside the CCD CMOS, so cancel. Next, in digital sensor, the saturation of pixels occurs when the exposure is too high, resulting in an area of image being completely white or black with no detail. This contributes to the phenomenon known as a option B, dose creep is the correct answer. Let's see the mechanism. So digital sensors have a wide dynamic range, meaning they can produce a usable image even if you overexpose the patient. The software automatically fixes the brightness so the image looks perfect on the screen. Now the creep portion, because overexposed image looks cleaner than the unexposed ones, the clinician often subconsciously increases the radiation dose over time to ensure they never get a bad image. And this gradual increase in the patient radiation without a diagnostic benefit is called dose creep. So let's see why not others. Option A, aliasing. So as discussed earlier, this is a wavy line pattern caused by a sampling frequency issue, not by high radiation dose. Option C, quantization. So this is the process of assigning a numeric value to the signal during the analog to digital conversion. It is a normal part of image processing, not an artifact of high exposure. And the image inversion, this is a software tool where you switch the blacks and whites of an image. It is a deliberate diagnostic choice, not a result of pixel saturation. So cancel. Next, which of the following digital imaging filter is used to increase the visibility of PDL space and lamina dura by highlighting the boundaries between structures? So the answer is high pass filter. As we discussed earlier, in digital image, filters are mathematical algorithms that change the pixel values based on their neighbors. So high pass filters This filter allows high frequency data to pass through while suppressing low frequency data. So high frequencies represent areas where the image intensity change rapidly, which is exactly what edges and boundaries are. So by enhancing the edges, it makes the thin radiopaque lamina dura and thin radiolucent PDL space stand out more clearly against the bone and the tooth root, and this is called the sharpening. Let's see why not others. Okay, so a low pass filter, this does the opposite. It removes the high frequency data and smooths the image. It makes the image look blurred and actually make the lamina dura harder to see. Then median filter, this is the noise reduction filter. We already discussed this. It replaces each pixel with the median value of its neighbor. It's great for removing salt and pepper noise but doesn't specifically highlight the boundaries. Option D, digital subtraction. This is a technique where you take two images of the same area at a different times and subtract the common parts. It is used to detect tiny changes in a bone density over time, not to sharpen the edges of single image. Next, in digital radiography, sampling refers to option C, measuring the signal intensity at discrete locations. Digitization consists of two main steps, sampling and quantization. So sampling, where an X-ray beam is continuous wave of energy. To make it digital, the sensor must sample it at a specific separate points. Think of this like putting a grid over a painting and looking at the color in each square. You are measuring the signal at discrete locations. Why not others? So option A, assigning a gray value to pixel. So this is a second step of digitization called quantization. Sampling tells you where the signal is and quantization tells you how dark it is by assigning numbers. So cancel. B, determining the number of pixels per area. So this is a result of your sampling choice, but it is not defining of the act of sampling itself. And D, reducing the radiation dose. This is the benefit of using the digital sensors, but it has nothing to do with the mathematical definition of signal sampling. Basically, in this step 1, choosing the locations to measure is sampling. Step 2, assigning a numeric color or gray value, which is quantization. Then two filters are used for enhancing edges, high pass filter, and removing graininess, low pass filter. If you want this PDF or any other PDF, like, share, subscribe the channel. Every update we generally post on community post section. Thank you.